Clare Kenyon, the Red Lipped Astro.
And I'm Mark Iscaro, the Drunk Astronomer, and you're listening to the Spaghettification Podcast, stretching your understanding of the universe. Before we begin this episode, we would like to say that in the spirit of reconciliation that we acknowledge the traditional custodians of country throughout Australia and their connections to the land, sea and community. We pay our respects to their elders past and present and extend that respect to all Aboriginal and Torres Strait Islanders people today.
So, what's this podcast all about? Well, pretty much everything. We'll tell you what's up in our skies each month, challenge you in our monthly astrophotography competition, and wander through some cool astronomical objects and concepts. We'll chat to some really cool guests, and finish up with a little segment we like to call Shit You Should Know, because, well, you should. First, let's talk about stuff we can see in the sky over the month of September. We should note that we're referring to skies in Melbourne, but many southern latitudes will be able to see these objects, albeit at different rising and setting times. Mark, tell us about our moon feature of the month.
This month's moon feature is Tycho.
I'm going to assume that you know how to find the moon in the sky. So tell me how to find Tycho.
So Tycho is located in the highlands south of the Nubian Basin. Sometimes I call it Mare, but I've been told I have to call it Mare. Mare Nubium, which is an impact structure that measures around 85 kilometres in diameter and about 4 kilometres deep.
So when I look at the moon and I look for Tycho, I look up and to the right.
Slightly.
And it's basically this great big white pimple. And you can see these streaks coming out of it. It's the sort of quintessential large moon crater.
It's fairly young. It's only about 108 million years old.
So do you know how they found out that it was about 108 million years old?
Through research from Apollo 17's mission. When they took a laboratory sample, they took samples and returned from the Apollo 17 lander.
That's actually right. So the samples that they've got are of melt glass. Basically, glass is just silica, and silica is found in moon rocks. So when there's something like a really big meteorite that hits the surface, it melts all the silica and forms this glass. And these samples were actually not taken from the crater itself. They were just thrown a very, very long way by this impact. And so the site where Apollo 17 landed and collected samples, they actually associated this melt glass that they found with this crater, which was quite a long, long way away. Now, Tycho is only 108 million years old, like you said, and then you said it's actually quite young. There's another way that we can know that it's quite young. Do you know what that is?
No, I don't. I'm going to learn here.
Oh, so you know how we were talking about the crater rays, the ejecta, the white powder that's sort of strewn out from these craters? Well, over time, exposure to the space environment actually turns that surface rock of the moon darker. So it becomes quite dark. And if you look around the moon carefully with binoculars or even just the naked eye, you'll notice that Tycho itself is actually not the biggest crater there. It's not sort of the most amazingly magnificent sized crater, but it sticks out because it is so white. All the other craters over time, all of their crater rays and their ejecta have actually become dark from exposure to the space environment over the sort of 3.9 billion years that some of them have been exposed.
See, I thought we knew Tycho was young because it was a teenager and it had a pimple in the middle.
Yeah, so this pimple's really cool. And actually
cool.
We expect that we'll find some melt glass down there as well. And it's basically almost like when you drop a stone into water and it goes down and then you see that little pimple that comes up on right in the middle where the stone fell while the ripples are going outwards. And that's kind of what we think happens. You sort of get this meteor that hits where the crater is and it melts all this rock and then it kind of goes bloop and comes up again and makes this little pimple. So tell me, Mark, exactly why do you like observing Tycho?
Why I like looking at Tycho? Oh, it's so prominent, and it was not many people know, but I like to say that I'm an astrophotographer, and it was just a part of the moon that I could practice imaging on with my phone through a telescope. So I spent a lot of time looking at it and looking for it. And I'd always wait for it to come back around each month so I could go, oh, it's back again. I can start trying to get my images better and better and better. And I just...
Even if they are upside down, Mark.
Even if they are upside down, it doesn't bother me because in space there is no way up. There's no right way up. Well, look, it's the right way round for me. It's upside down for everyone else, and that's fine. But,
are you only good at sports, Mark?
You're
seeing the ball coming from the opposite direction all the time?
I was okay at swimming. Tennis, couldn't kick a football to save myself and couldn't see it coming. I get bowled out a lot very easily as well in cricket, so that says a lot, doesn't it? Don't know where the ball's coming from.
We could ask our upcoming guest's brother-in-law. So we're going to ease into our constellation of the month with a very well-known constellation. You might know of it as the Southern Cross, otherwise known as Crux, and there's quite a famous little asterism in there. Mark, can you tell me what an asterism is?
It's when you see an image of something in an object that isn't really there. So what's an example of that? So the asterism you're talking about in this, in the Southern Cross is the cross. So people see it as a cross or as a constellation, but it's not actually a cross. Those stars are nowhere near each other.
But that's the same as constellations, right?
Yeah, so it's all constellations are asterisms.
Yeah, that's actually true. All constellations are asterisms. That is, they're basically pictures or patterns that we see in the stars. But constellations themselves are designated by the International Astronomical Union, or IAU. So pictures in the stars, right, is probably a good way to summarise that. We like to find patterns. Us humans like to find patterns, like the face in Mars and the man in the moon and all those sorts of things. So patterns have always been a big part. Pluto and Pluto.
Pluto and Pluto.
Oh, the dog.
Yeah.
Right. I was like another like you mean the dwarf planet and the dwarf planet? So human beings tend to like looking for patterns, and that's why the Southern Cross, or Crux, has been part of many Indigenous stories as well, all across the world, including our First Nations people here in Australia.
You're right. So to the people of the Central Desert, the Southern Cross represents the footprint of the wedge-tailed eagle, and the 2 pointers are his throwing stick. However, to the Burong people in Victoria near Lake Tyrrell, it represents Bunya the possum.
The cross consists of 4 stars, and you've got this really bright blue-white one, the most bright one that you can see in the constellation of 4. That's the most southerly member, and that is called Alpha Crucis, or A Crux. We have 3 more stars in there. Beta Crucis is also called Mimosa, Gamma Crucis, Ga Crux, and Delta Crucis, Ime. There is actually a 5th star within the constellation, but it's not actually part of the asterism, called Epsilon Crucis, or Guinan, and you can often see that as the 5th star in some flags as well. Inside the constellation Crux, or the Southern Cross, there are also what we call Cepheid variables, and there are 4 of these. And Cepheid variables have had a really important part to play in us being able to understand the size of our universe. And we're going to talk about that in depth in another podcast.
Back on asterisms, and we're talking about Bunya the possum. So he can be seen sitting in the tree in the constellation of the Southern Cross. With the tip of the Southern Cross is the nose of the possum, and his tail hangs down to the left. So essentially, Bunya ran away from Tingal, the emu, and hid in a tree for so long that he turned into a possum. And the emu is obviously another asterism or indigenous constellation. That's a constellation of dark spaces in the night sky. So it's all linked in to the one story.
Unfortunately, the Southern Cross is not actually visible to people a long way north. So when you're really high in the Northern Hemisphere, unfortunately, you can't see the Southern Cross. I'm sorry. Luckily, we can see it all the time. People in the Southern Hemisphere can see the Southern Cross all the time. And did you know that it wasn't actually always like this? The Southern Cross actually used to be visible to people in the Northern Hemisphere quite far north, as far as Britain. And in fact, it's been written about by the ancient Greeks. And what's really interesting is that over that time, from the ancient Greeks till now, which is really only just a speck, of sand on the beach of universal time, that now it's not visible. So the reason that's come about is actually because of what we call equinox precession. Essentially, that's to do with the Earth on its pole and that pole slowly precessing in space, a bit like a top, the axis of a top. And Mark, I reckon that might be another good topic for a podcast.
I think it would, because do you know the last time the Greeks saw it? It was 400 AD was the last time the Greeks or, the Northern Hemisphere saw crux.
Well, it's all ours now. Nobody else can have it.
No. Well, it's not necessarily just ours. There's a stone image of crux in Machu Picchu in Peru.
No way.
Yeah, and the Inca knew the constellation as Chacana, which means the stair, and the Maori called it, and I'm probably going to get this wrong, Tapunga, which is the anchor.
Wow. Yeah, really culturally significant to a very large number of people.
Very much so, yes.
So, Mark, a bit closer to home than the stars in Crux, we're going to give you a planet report for the month. And lucky us, 7 of the 8 planets are visible this month, but maybe not that easy to see.
I'd like to think that one of those is very, very easy to see. Hopefully.
Do you mean in a way that we're sort of standing on it?
That we might be standing on it, yes.
Yes.
The other ones that are nice and easy to see at the moment, obviously Venus is like almost as bright as the sun at the moment over in the west.
Do you mean almost as bright as maybe the evening or the morning star?
Yeah, yes. Yes. My dad joke was even worse, I know. The other ones that are pretty good to look at the moment, if we can get some clear skies, we haven't had a lot of clear skies lately, but if we can, Saturn is looking magnificent at the moment, and Jupiter as well is looking lovely. In fact, when we finish recording this podcast, if the skies are still clear, I'll be out there trying to image the two of those.
And of course, you'll be posting those pictures up for us to have a look at.
Oh, absolutely, I will. I'll be posting those at Drunk Astronomer on Instagram, and I'll be tagging Spaghettification on Instagram.
So I just wanted to point out here that if you're a little bit unsure about how to find a planet, apart from the fact that they always go from east to west, they always rise in the east and set in the west, depending on where you are on Earth, they might actually emerge out of the dusk already in the west. But essentially throughout the day, they travel on what's called the ecliptic. So that's the path of the sun. And the planets all travel roughly on that line as well. So you can always expect, if the planet is rising at 8 p.m., for example, look over towards the east because that's where it's going to be coming up. And then if it's setting, look over towards the west, just like a setting sun. It'll be over there. But if you're still not quite sure how to find a planet, on the 17th, there'll be a conjunction of Saturn and the Moon. And then on the 18th, there'll be a conjunction of Jupiter and the Moon. And then on the 25th, if you're very good at finding planets and you know what you're doing, you might even be able to see a conjunction of the Moon and Uranus. Who would have thought that the Moon and Uranus were going to have a conjunction?
Can this be our photo competition? Can you imagine the photos we would get?
Wow. Let's all be really creative, shall we? I don't want to be kicked off air straight away. So a conjunction basically means that they're going to be very, very close in the sky. The other word, I suppose, for being close in the sky is an appulse, and it's not exactly the same. A conjunction strictly means that they share the same right ascension. So we sort of divide the sky up into latitude and longitude, much like we divide the planet. And depending on where you are on Earth will depend on exactly the coordinates in the sky that we see. So just expect Saturn and Moon to be on what we call the same right ascension, which means they'll just be very, very close. Unless you know your right ascension, it probably won't help, but they'll be very, very close in the sky. Not necessarily close enough to look through the telescope, but certainly close enough for you to be able to find Saturn, find Jupiter, and know that you've actually got it.
Can I ask a question about the ecliptic? Does that change with the seasons, sort of towards the north, south? Sometimes Mars looks like it's lower when it rises, and sometimes it looks like it's rising closer towards the east.
The ecliptic is basically the path that the sun travels. The further away from the equator, the more obvious this is. In the winter, the sun never really quite gets up to directly above 90 degrees in the sky, which we call high noon. There's only one day of the year that it's there, right? And when we get into winter, the sun, from Melbourne at least, gets lower and lower in the sky and actually sets in a different place. It rises and sets in a different place to where it does at the height of summer. That's the ecliptic. It's the path that the sun travels across the sky, but projected into the night sky. And the reason the planets all follow this same ecliptic path, and I feel like this definitely should be an in-depth at some stage for another podcast, but the reason the planets all follow the same path is because we're all on the same plane, pretty much, give or take, as the sun. So we all sort of go round in a disk around the sun. And that's mostly to do with how we think the solar system actually formed. And that is basically all together by gravitational forces condensing out of a disk. So it would make sense that it sort of all goes around in the same plane. And if you want to know what a plane is, have a look at some of those cool bicycles that they've had at the Olympics recently, where you've got that really thin disk that comes radiating out from the center axis all the way out. And it's this disk, really, really thin. That's essentially what you can imagine all the planets sitting on, except obviously it's not metal in between, it's space. And not empty space at that. Okay, so for all you comet hunters out there, there's a comet called 4P Phae that will be reaching perihelion, that is, its closest approach to the sun, on the 10th of September. It should be visible in the north, although fading, throughout the end of September. You're probably going to want to have a look on a few websites to check out its actual path, because it's never quite 100% predictable, and also the brightness is never predictable. But if you're a comet hunter, this month, this one's for you, 4P Phae. 4P Phae is a periodic Jupiter family comet. It's been known about since about 1843, so, only a small amount of time. And it last came to perihelion on May 29th, 2014, and will next come to perihelion on September 10th, 2021. And then after that, can you guess, Mark, what year the next one will be? How's your 7 times table?
I was going to say, is it 7.43 years from now?
Something like that, yeah. So 2028, we can expect it again.
What a guess.
And so this is why we call it a Jupiter family comet. It's got quite a short period, not like one of these amazing ones that we don't see for hundreds of thousands of years that have come from far, far, far out in the solar system. This one just kind of circles around and comes back. It's not very, it doesn't go very far. And this comet has actually been seen at every return since its discovery. It had a couple of really poor ones in 1903 and 1918. But actually, it's there and visible most times it comes about. Every 59.3 years, this comet actually gets a little close to Jupiter just because of its sort of eccentricity in its orbit, which means its irregularity in its orbit. This comet sort of just gets a bit too close to Jupiter, and Jupiter gives it a little bump, a gravitational bump, which sort of changes its orbit quite a lot. And that happened in 2018. So we're actually not necessarily 100% sure what the long-lasting effect is every time this happens, every sort of 60 years. Every time it gets bumped, it could go somewhere else. Not that far, but, it changes its orbit enough to actually keep knocking it in closer and closer and closer.
Could Jupiter swallow it up at some point?
Interestingly enough, every time it gets bumped, it gets a little bit more eccentric. So I don't mean like, Mark, that it has green hair. I mean, it's eccentric.
Nothing wrong with that kind of eccentricity.
So eccentricity can be thought of as...
Can be thought of as your co-host having lime green and teal blue hair?
It could be thought of as your co-host having lime green and teal blue hair. Eccentricity can be thought of as how much an oval is a circle. So what I mean by that is a circle has 0 eccentricity. if you had a piece of string in the shape of a circle and you pulled the end slightly, you've made the circle a little bit more elliptical. You've made the circle less of a circle, more of an ellipse, more of an oval shape. This is eccentricity. So a circle has 0 eccentricity. Ellipses have eccentricity values anywhere from above 0 to 1. And so what happens every time Comet 4P Phae, not the same sort of ring as Halley really, every time Comet 4P Phae gets close to Jupiter, it gets a kick, a gravitational kick, which sends it a little bit closer and makes it orbit a little bit shorter. But balancing that on the other side is the eccentricity goes up as well. And so there's actually a resonance of the period of the comet and Jupiter, which is 8-5. So I don't think, unless something happened for the next, 100,000 years, I'm not really thinking that's going to happen anytime soon. All right, Mark, on to 47.
47 Tucanae. 47 Tuc. This is a favourite.
Tuc or Tuk? I mean, you say Tucanae, but then you say Tuc.
I know. The deep sky thing. We could just call it 47 Tuc.
Private in-joke.
Yeah, well, I don't know if it's an in-joke. It's just when we go, we'll have a look at 47 Tuc, eh? It's just we've kind of occified it.
Occification.
47 Tucanae.
Tell me about it.
Well, there is another one near it that you can get confused over. I can never remember what its name is, what its NGC is, but I will have to go away and do some research and come back on that one because it's quite interesting as well. But it's a globular cluster in the constellation of Tucanae. It's about
14,800 light years.
Well, some say different.
Some say.
Now we'll say 15,000 light years roughly, hey?
Yeah, just under. That'll be fine.
Yeah, just under.
It's probably within error anyway, right?
It is within error, give or take. It's about 120 light years in diameter. And if you're at a dark sky site, you can see it naked eye. And I have seen it naked eye at the dark sky site I go to.
That sounds a bit rude.
Yes, I take the clothes off my eye and stare at it. You can just make it out a little fuzzy sort of patch. You can confuse it for a star. Same as Omega Centauri as well. Confusing it as a star, sometimes like a fuzzy star that a bit of cloud might have gone in front of. In fact, I think it's a better object than Omega Centauri. I think it's a much nicer globular cluster to look at.
So from an astrophysical perspective, what's cool about this globular cluster, so just going to tell you what a globular cluster is for 5 seconds, so if you already know this, just ignore me.
Okay, I'll ignore you.
Globular cluster, excellent. A globular cluster is a tightly gravitationally bound cluster of stars, and they're called a globular cluster because they're usually quite spherical because gravity holds them quite close in this sphere. Now, what's really cool about this particular globular cluster, 47 Tuc, is that the interior, it's so tightly bound that they actually think that it's home to neutron stars, more specifically millisecond neutron stars, millisecond pulsars, which we actually have a guest coming up, probably next episode, who does actually mention millisecond pulsars in his interview, which is absolutely fantastic. That's Paul Lasky. And millisecond pulsars are basically neutron stars with a bright beam of radiation that sweeps past Earth, but they get sped up usually by binary or companions. And so this globular cluster is actually thought to be home to millisecond pulsars. So they think this is where they're all forming. And they're really, really, really cool. So there's also a really, really close pairing of stars there. So there's a binary star in there called X9 because, it sounds a bit like X-Men, I guess. And they think it's a white dwarf orbiting a black hole, right? So a white dwarf is a remnant left over from a star kind of probably about the size of our sun or a little bit more after it's sort of puffed out its outer layers in a planetary nebula, which we'll be talking about shortly, and left this little white dwarf remnant star. and a black hole, which, is at the end of a massive star's life where gravity is just so intense, there's so much mass that space basically caves in on itself. So these two things are orbiting each other, Mark. Have a guess at how long it takes for this white dwarf to go around the black hole.
Oh, I'm going to have an absolute random guess, and I'm going to say maybe 20 minutes.
You're so close.
Oh,
it's
really?
25 minutes. Insane.
What a guess.
25 minutes for this white dwarf, a star, right, to go around a black hole. That's how close in they are orbiting. So they really don't know how this formed. They think that possibly the black hole smashed into this red giant. So a black hole comes along, just smashes in, goes, "How you going, mate?" Smashes this red giant apart, and the outer regions and the gas was actually ejected. The remaining core of the red giant makes a white dwarf, and that black hole, it becomes a companion. And then they'll be very, very close, and the orbit shrinks as gravitational waves are emitted. So it actually loses energy and starts orbiting closer and closer. There are other explanations. They think maybe that the binary is actually a neutron star rather than a black hole. But this actually doesn't seem to be what the data's saying. It actually does look like there's a white dwarf that goes around a black hole in 25 minutes. So globular clusters are cool. They tend to be about, maybe 10 billion years old plus, at least the ones in the Milky Way.
This one's meant to be 13 billion years old.
Yes, exactly. So that's why we actually see old stars. So globular clusters tend to be about 10 billion years old in the Milky Way, and then that means that they basically have some of the oldest stars and make them so fascinating as astrophysical targets for research. They usually have a lot of yellow and red stars because they're the ones that are longest living. So low mass stars tend to last a long time. I make the joke that they're kind of the accountants of stars.
Boring. Where's the rock stars when you need them?
They exploded a long time ago.
They all got to 27 years of age and disappeared.
Yeah, that's a crazy number, isn't it?
It is a very crazy number.
Nuts.
Very crazy number.
Hey, you could talk about how to find it. It's right next to the Small Magellanic Cloud.
It's not far from the Small Magellanic Cloud, and it's about the size, roughly the size of the full moon in the sky when you're looking at it under good conditions as well.
So naked?
Yes. Yep. Stripped down, naked, running rampant through the dark sky at the Astronomical Society of Victoria, which I'm sure has been done before, but not by me.
Oh, okay.
No,
nothing to see here, folks.
No, I'm
Literally
not that
nothing
game.
to see here.
I'm game, but I'm not that game. Too many security cameras up there.
So our next target is our planetary nebula of the month. An object in the sky that is so beautiful it has its own category, planetary nebula. We're going to be talking about it in depth shortly. And it is also the subject of our photo challenge this month. So the Dumbbell Nebula. Dumbbell. Tell me about it.
Well, I reckon it's more like an apple core than a dumbbell. But it was spotted by Charles Messier when he was comet hunting, and he went through and trying to find everything in the sky that wasn't a comet, and this is one of those objects. So he discovered it in 1764, and as Claire's saying, it's a planetary nebula, but it's not a planet, but it is a nebula. So it has a round-like shape when you look through it through a telescope. And it's essentially an old star that has just gone boom and kicked off its old layer of skin, I guess. I've seen it visually through my little telescope. I've seen it visually through some of the larger telescopes. In fact, I have kind of imaged it with my phone, not very well. But it's a beautiful object to look at. It's a favourite for live stacking when I do live streams. I get the guys to live stack it because it comes up so quickly and you can really get the shape and definition of the object in a few minutes worth of exposure. It's just a lovely object. It has some really nice colour in it as well.
Okay, so let me tell you a little bit about the star at the centre of this planetary nebula. So the planetary nebula is enormous and really, really good to see, as Mark mentioned. It's actually the faint halo, the very outsides of it, is about half the size of the moon. So it is one of the most amazing things to see in the sky. Right at the center of this planetary nebula, the one that kind of caused all of this gas, is quite bright. It's Mag 13.5. It's extremely hot, this star. It's a blue subdwarf, probably about 85,000 Kelvin on the surface. So this is what we call an O7 type star. Our sun, the surface temperature, just for some calibration for your minds, 5,500 is our sun's surface temperature. And this one is 85,000 Kelvin. Insane. Really, really, really hot. So if you look right in the center of this planetary nebula, don't be surprised to see a bright, glowing blue star. So how do we find it if we want to go looking for it?
Now, finding it at the moment is you're going to have a pretty clear view to the north. And then what you want to do essentially is sort of come down from Altair, bright star in the north sky. And if you know your stars, you've got Altair and then you've got Vega, which is very low on the sort of northwest horizon at the moment. And then it would be around about 1/3 of the way down from Altair, slightly to the, well, sort of almost directly north. That's where you're going to find it at the moment. The people who are going to be taking an image of this are going to be astrophotographers, that's for sure. Some of them may have already taken an image of it. No previous images are allowed to be entered into the competition, are they, Claire? Or can they be previous images? Or do they have to be...
I think if you've published it, I reckon no.
All right, so if it's a published
already, we'll
image,
say no.
No. So if it's a non-published image, then yes. And I know these guys like a challenge. So this is a challenge for them at the moment to get a nice image of Dumbbell Nebula.
Yeah, so basically you've hit on our little next segment that we're going to do each month, and that is our astrophotography competition. So we are going to challenge all of you to take a creative picture. It can be however you like, take creative on board. It can be absolutely beautifully coloured. It can be whatever artistic interpretation. It can just be amazingly, beautifully stark. We don't mind.
It could be
whatever
drawn.
you
It could
want
be
to
hand-drawn.
submit.
No,
it's got to be a photo, Mark.
Oh.
Come on.
Could it be a hand-drawn sketch with a photo taken of it?
I think if you submit them both, let's just open it to creativity.
Creativity.
So this competition, exactly. So submit your photo, your best photo you can of the Dumbbell Nebula, preferably taken this month in these skies. So not allowed to be published anywhere else before now. You need to submit it to us. Every month you can upload your submission for our astrophotography competition, and we do actually have a monthly prize. The monthly prize will be decided by viewer votes. Of course, Mark and I will have a viewer vote or two. But what's the monthly prize?
The prize for our photo competition is a pair of Saxon 10x5 multi-coated optics binoculars supplied by our sponsor, Sidereal Trading. Sidereal Trading have strong emphasis on quality products and service-oriented sales and technical staff. Sidereal Trading's key strength is their ability to work closely with customers to achieve the results they desire. So whether you're interested in nightscape photography, panoramas, wide-field Milky Way or deep sky nebula and galaxy, Sidereal Trading can supply the astrophotography equipment you need. For more information, visit siderealtrading.com.au.
So basically, get your telescopes out, get your cameras out. Happy hunting.
Happy hunting. In-depth planetary nebula. Take it away, Claire. Tell us a little bit about planetary nebula and what they are. And I think I might throw in, somewhere along the line there, some of my favourite planetary nebulas that I like to look at.
That'll be awesome. And they'll all be formed in much the same way. So planetary nebulae. Nebulae, of course, is the plural of nebula. So if you hear that, it's not just me having a stronk. It's me saying plural, nebula. So planetary nebulae are nothing to do with planets. And a nebula, of course, if you're new to this, nebula is sort of dust and gas, mostly gas up in the sky that sort of glows with the light of either itself because it's excited or it reflects light. So these are called nebulae. You can see them in sort of gassy areas in the sky, and they can make the most beautiful views. And planetary nebulas, I think, are some of the finest views we can get of our skies, and which is why we've actually devoted a whole segment every month to our planetary nebula.
I would absolutely agree that they are some of the most beautiful objects in the sky.
They truly are, and they have the most varied shapes and colours, and there are cat's eyes, there are cat's paws, there are, whatever you want to find, you'll find it. They're ghosts, apparently, of Jupiter, which we will touch on in another podcast because it's Mark's favourite.
Absolutely is.
It's a shame it's not up at the moment.
No, it's not.
So what are they, right? They're nothing to do with planets at all. They're actually at the opposite end of a star's life cycle. A planetary nebula is produced when the outer layers of a normal medium-sized star like our sun, at the very end of its life, the outer layers puff off. And that puffing off is actually the gas we see as a planetary nebula. So how does this actually happen? Well, when the sun's in its normal phase of life, it's busy pushing protons together, or hydrogen nuclei together, to make helium. And this process produces a lot of energy, which eventually makes its way all the way to the surface of the star. And this actually creates a pressure on the outside of the star layers, keeping the star up. We've got gravity of the star pushing in, immense gravity, like we're talking the mass of the sun, immense gravity pushing into the centre, which is what forces the protons together, and also this radiation pressure pushing the star's layers out. Eventually, at the centre of the star, the hydrogen runs out. And you're like, uh-oh, now what? Because if the hydrogen runs out, we've just got helium, right? And there's nothing to push these layers out, right? So what happens? Well, the star actually contracts a bit. It actually gets a little bit smaller, and this is the part that you don't really hear about. The star actually contracts a little bit so that the helium can be forced together. Now, when that helium gets forced together, you start to actually ignite hydrogen in the outer layers outside the normal center part of the sun. You start to get what we call shell burning. And that, plus the helium fusion in the center, actually causes the star to expand because there's a lot more radiation now. So you've got all this burning going on, they've got a lot of energy coming out, and it's in this sort of wobble phase. And the shells actually start to move out and out and out towards the edge of the star. And we've got helium going on in the middle, and if the star's massive enough, it moves up to the next element. The next element may be carbon, maybe oxygen, eventually finally finishing at iron and nickel, never further. But anyway, so we get the shell burning all the way out, and the star starts pulsing. Okay, because it goes in with gravity, goes out with radiation pressure, it goes in with gravity, out with radiation pressure. And we call this the AGB phase. No, not the AGB that we are all thinking about right now. No, we're talking about the asymptotic giant branch phase. And that means that it's basically in its death throes. This star is pulsing in under gravity. It ignites again, it puffs out. It goes in under gravity, ignites again in the shell, and it puffs out. And each time it puffs, we think that actually makes these layers of gas and dust, which puff out really slowly and make basically the beautiful gases we see now. At the very end, once it's finished puffing all this stuff away, at the very center is left a burning white dwarf. This white dwarf is not fusing anymore. It's actually just producing energy due to gravity. So essentially the gravity's pulled the rest of whatever's left into this tiny ball of material. And it's this gravitational contraction that makes the energy, that makes these white dwarfs glow so brightly and so hotly. They also create a whole bunch of stellar winds which puff and blow this gas even further out, right? So that's the gas that we see. And I bet you're sitting there thinking, hey, shouldn't this be spherical? Well, just recently, people have actually found that planets play a huge part, and binaries, anything else gravitational in the area, play a huge part in the shapes that we can see. So it's actually thought that when the sun finally experiences this phase several billion years from now, Jupiter and Saturn and some of the other bigger planets will actually play a major role in shaping whatever our planetary nebula is going to look like.
I was going to say, when you're talking about it puffing out and contracting back in, almost like it's trying to take its last breath.
Yeah, it's in its death throes.
It's struggling for breath. It smoked too many cigarettes, probably.
So another way that you can think of planets and other sort of small stars, so low mass star binaries and heavy planets interacting with the planetary nebula, I've heard it talked about like it's a spoon stirring coffee.
Ooh.
So you can sort of stir them, obviously milk coffee, not a black one. You stir it and you can kind of get these spiral patterns. You get the sort of dumbbell shapes or apple core shapes or eye shapes, some of the most amazing, pretty things we can see. Shit.
You?
Should.
No.
Because you should.
Absolutely should.
Well, today we're going to have a look at something called a day. You think you know what that is?
It's got 24 hours in it. I know that much.
Oh, close enough.
And a bit.
And a bit? Or a bit less? Which one is it?
A bit less. Bit less. Bit less?
Is it? Are you sure?
Oh, you're confusing me now.
Good.
I'm easily confused.
Yeah, the drunk astronomer is easily confused. It's true. But actually it is a fairly confusing thing because there are two types of days.
Only two?
Well, I'm sure there are probably more. You know, there's a bad day, there's a hump day, there's all these other types of days.
Between the two of us, I thought there was only one day.
One day you'll understand.
So what are these 2 days? 2 types of day?
So it comes down to how we count time. Imagine if you could just stop Earth for a moment. Hit pause on gravity for a little while and stop Earth in its position in space. So stop it orbiting the sun. We're still going to let Earth go around on its axis. We're not that horrible. We don't want to give some people permanent night. Here we are, sitting pretty above the solar system, looking down at the sun in the centre and the Earth turning on its axis, but not going around the sun right now. Now, imagine drawing a little dot on the Earth that is on the side that is directly facing the sun. Okay, let's turn the Earth a full 360 degrees anti-clockwise, because that's the way it turns as viewed from our current orientation. We'll call this a day. A solar day, the time taken for Earth to turn 360 degrees and for that spot to be in the same position again, which is directly facing the sun. All good? Right. Let's have a quick look at the other side of the Earth, the side that is in nighttime while your dot is facing the sun. Imagine drawing a little cross there, exactly on the other side of the globe to the one facing the sun. Now, let's pick a point, a star. Let's go with a long way away star. So a very distant star.
The sun?
No. So the sun's our closest star, Mark. We'll pick one that's much further away. Okay, so we pick a distant star. The furthest star. And yes, I know furthest is not a word, but for the purposes of explaining to the 5-year-old drunk astronomer,
I'll be 6
it's
soon.
a word now. You're going to be 6?
Yeah, I'll be 6 soon.
Nearly 6.
Nearly
okay.
6, yeah. So what is this furthest star?
Do you want to pick a star?
Let's just go Altair.
Okay, so let's go with Altair, all right? So I'm not sure, Mark, but is 16.73 light years far enough away?
Well, I hope it is. For the purposes of what we're trying to explain, I would like to think that it's far enough away.
Okay, so Altair is 16.73 light years away. It takes 16.73, almost 3/4 of a year, for light from Altair to get to Earth. And light travels at, 2.9988 times 10 to the 8 metres per second or something?
I'll just say yes.
Big distance, good. Okay, back on topic. Someone is standing on your cross on Earth's night side, and looking at this star. How long does it take for that star to be in exactly the same spot with respect to the cross? Yep, at the moment it's the same as the time for the sun and your dot. A day. This method of using the stars to time a day is called a sidereal day. Right, let's set Earth in motion around the sun again. It's still spinning on its axis, but now it's going to go back to orbiting the sun, which we know takes around a year or 365 days to complete. From the vantage point of above, where we're sitting and watching, the Earth orbits the sun in an anti-clockwise direction, as well as spinning on its axis in an anti-clockwise direction. Now, every time the Earth completes a true 360-degree turn, it actually has to turn just a little bit more on its axis in order to be able to put the sun and the dot in the same position. So to see the sun in the sky again from that dot, it actually has to go a little bit extra around its axis. This is to account for the step forward along its orbit that the Earth has taken. The Earth needs a little bit of extra turn each time. So, turn 360 degrees whilst moving forward, turn a little bit extra, and then the sun is overhead again. This is our solar day and is approximately 24 hours. I say approximately because the orbit of the Earth is not a true circle, it's an ellipse. Its eccentricity, if you remember our conversation earlier, isn't 0. But we'll keep this for another day. Now, let's examine the cross on the night side of your Earth. It's looking at a distant star, like really, really distant, ultra distant.
Yep.
So distant that the distance from the sun to the Earth is pretty much negligible. So distant that the movement of the Earth around the sun over a whole year is basically undetectable. Relatively nothing. It's as though the Earth is sitting still in space, which takes us back to our original scenario that we imagined before. This is a sidereal day. So, you've probably worked this out. A solar day is a little bit longer, by about 4 minutes, than a sidereal day because the Earth needs to turn a little bit extra on its axis to account for that little bit of motion forward it has made as it orbits the sun. Whereas if you use a very distant star to count a day, there is effectively no transverse or lateral movement at all of the Earth and no extra time needed. So there it is. You now know the difference between a solar day of 24 hours or thereabouts and a sidereal day, which is around 23 hours, 56 minutes and 4 seconds, almost 4 minutes shorter than a solar day.
So what you're saying then is if Altair rose at 9 o'clock tonight, then tomorrow night it would rise at 8:56 and the next night it would rise at 8:52?
Well, basically, yeah. And this is kind of why we see different constellations and different planetary nebula and different things that we want to talk about each month. This is why we see different things in the sky throughout the year.
So what do we call that time?
So that time is sidereal time. So we've got solar time on one hand, which is when the sun appears in the same place. That's the 24 hours that most of us are familiar with. And then we've got sidereal time, which is how long it takes for the same star to appear in the same place in the sky each night, from night to night. Sidereal time.
Who are also our sponsors this month.
Sponsors of our photography competition?
Sponsors of our photography competition.
Sidereal Trading can supply the astrophotography equipment you need. For more information, visit siderealtrading.com.au.
Hey! Subscribe, sponsor or support us. Head along to our website at www.spaghettification.com.au, that's spaghettification.com.au, and follow the links to subscribe. Photo submission for the astrophotography photo of the month is through our website. Check us out on YouTube and Instagram, and keep an eye out for submitted photos which need your vote on our Instagram page. We now have a Patreon, which gives you special access to extra behind-the-scenes content, bloopers, and potentially a guest spot on the podcast. If you'd like your name or business featured in a podcast, hit us up at spaghettificationpodcast@gmail.com. All right, Mark, so that, unfortunately, is all we have time for today. Next episode, we are lucky enough to interview Paul Lasky, who's an astrophysicist at Monash Uni. His particular focus is gravitational waves, and as we mentioned earlier, has had a bit to do with neutron stars, black holes, and all cool things. So tune in to hear that. And don't forget to submit your astrophotography competition photos.
And just remember, next time you look up at the night sky and see all those pinpoints of light, remember that they are each a unique furnace of nuclear processes at different stages of their life cycle.